as we saw in the preceding, the gravitational field, the gravitational acceleration of the comet, the gravitational field of the comet, which is the gravitational acceleration at distance r from the comet, is 1 over 4,000 cubed times g mass of the Earth over r squared. The 4,000 cubed, 1 over 4,000 cubed, is the ratio of the volumes of the comet and the Earth, the ratio of the volume of the comet to the volume of the Earth, and will be equal to the ratio of the masses, the mass of the comet to the mass of the Earth, so that we can replace mass of the comet here with 1 over 4,000 cubed times the mass of the Earth. We want to compare g, though, at the surface of the comet to g at the surface of the Earth, and that means that the r at the surface of the comet will be 1/4000th of the r at the surface of the Earth, and that's going to tend to increase the result for the gravitational acceleration, because at the comet we can use a much lower r, which is much bigger, which is going to result in a much bigger result than it would if we'd used the radius of the Earth. So let's see how that works out. So what's the ratio? Okay, well, the ratio could be written as gravitational field of the comet at 1 mile over 9.8 meters per second squared, which is the gravitational field at the surface of the Earth. And it's going to be useful to keep that in mind. But we're going to go here now. We're going to just say, well, okay, the gravitational field of the comet is, as we saw, 1 over 4,000 cubed g mass of the Earth over 1 mile quantity squared. The gravitational field of the Earth is g times me over the radius of the Earth, the distance from the Earth to its surface, 4,000 miles. So we're going to have 4,000 miles squared in the denominator here. When we work this out, this complex fraction, inverting the denominator and multiplying, the g, big G, big ME are going to divide out, and we're going to end up with 4,000 miles quantity squared over 1 mile quantity squared, which is going to be 4,000 squared, and that divided by the 4,000 cubed is going to give us a ratio of 1 over 4,000. And 1 over 4,000 tells us that GC of 1 mile is approximately equal to 2 millimeters per second squared. Now, actually, if you divided it 4,000 into 9.8, you get something closer to 2.5 millimeter per second squared. It would round off to 2.5, but I'm just going to use a whole number, and I'll mention that's appropriate because the comet is elongated. Okay, so it isn't a perfect sphere. It probably has a density less than that of the average density of the Earth, more akin to the density of the crust of the Earth, as I mentioned on previous, on the immediately preceding clips. So what we're getting here is probably still an overestimate. Still, we're going to use this and see what the implications are. Now, okay, the probe hits the comet and bounces. It takes an hour for the bounce to occur, okay, for the comet to go away, or for the probe to go away from the comet and then come back. So it's reasonable to ask how fast it was going when it just as it bounced off, okay, at the beginning of its bounce. Now, it's going to bounce off and it's going to be slowed by the comet until its velocity is 0, and then it's going to come back down. I actually followed a parabolic path, but the up and down motion is still going to be the same as it would be if you assume the spherical model. And of course, we don't, spherical model is not totally accurate. And that is another reason that actually this probably is an overestimate. And 1 millimeter per second squared might be closer than 2. Still, using the 2 millimeter per second squared, the question becomes, how much velocity did it lose in the as it rose away from the comet, as it moved away from the comet? Well, again, the bounce took an hour, so we're going to ask at 2 millimeter per second squared, what would be the change of velocity in half an hour? the change in velocity is going to be the same, the magnitude of the change in velocity is going to be the same as the initial velocity as it bounced off, which we assume is going to be somewhat less than the velocity it had as it approached the comet. Okay, so let's see, 2 millimeters per second squared in 1800 seconds, which is half an hour, that's easy enough, is going to give us 3,300 millimeters per second. This is a straightforward calculation. We don't have to look up formulas or remember formulas. We just have to remember what acceleration means. So we can make this very intuitive calculation and get 3.6 meters per second as the change in velocity, meaning that it bounced off of the comet at 3.6 meters per second. Now that's not totally consistent with the idea that it approached the comet at walking speed. Okay, that's greater than walking speed, but it's not out of the ballpark greater. The walking speed, again, between 1 and 2 meters per second. So this is maybe twice as great as the upper end of what we would regard as walking speed. Given that this is an overestimate of, that I believe this to be an overestimate of the acceleration of gravity at the point that the probe actually bounced off, that makes this the whole model pretty reasonable and consistent with the idea that it approached the comet at walking speed. Question, how far would it go in half an hour? You should pause, as you always should when a question is posed, and think it through yourself. In any case, well, its average velocity, if you assume acceleration to be uniform, which it certainly is not, but let's make that assumption. Assume v bar is 1.8 meters per second, so the delta s would be about 3,200 meters. Okay, just multiply the 1.8 meters per second by the 1800 seconds. You get 3,240 meters, approximately 3.2 kilometers. That's fairly comparable to the radius of the planet, but it gives the lie to the idea that we have a uniform velocity of 1.8 meters per second. This is greater than the radius of the planet, probably 3 times as great or twice as great as the radius of the planet, meaning that our gravity would be down to 1/4 of what it was at the surface, even with the spherical model. And again, we're not even going to try to analyze the model for the irregular comet. So that I'll make a note here. Acceleration is not uniform. This is not a good model for delta S. But what this means is if the speed at the bounce is 3.6 meters per second, the lander would have bounced much more than the 3.2 kilometers, meaning that the speed was probably a whole lot less than 3.6 meters per second, putting it into reasonable walking, into the range of reasonable walking speed again. So, without going any more deeply at this point into the model, we'll leave it at that. We have a plausibility argument here that the 1 hour bounce is consistent with an approach at walking speed.